Hello and welcome to this video on trebuchet physics, design, and tuning. Keep watching and I'll not only teach you trebuchet physics, I'll show you how to make an efficient trebuchet and improve the distance of your throws. So how should we view a trebuchet? Many people see it as an uneven teeter-totter. You see this in plenty of movies, but a trebuchet operating purely as a lever won't throw very far. I'll show you several tricks or energy transfer mechanisms that will allow you to throw farther. It's probably best to start with a review of conservation of energy. Let's say that I have a stationary counterweight on a frictionless ramp. This counterweight is height h above the bottom of the ramp and has mass m. It will start with potential energy mgh. At the bottom, it will have kinetic energy 1/2 mv squared. By conservation of energy, E equals mgh, which is also equal to 1/2 mv squared. We can add a second object to represent the projectile and accelerate it from a velocity of 0 to v2. We do this by somehow transferring energy from the falling weight to the projectile. This adds the projectile's kinetic energy to our equation. Now we have to divide the energy between the counterweight and the projectile. In other words, the projectile is fastest if the weight is stationary at the end. This creates a very simple rule to judge success. If your arm and counterweight are moving fast at the point of release, then you are probably doing it wrong. I'm going to show several energy transfer mechanisms. Together, these will transfer most of the energy from the counterweight to the projectile. I'll start with a lever, which is an important feature of all trebuchets. Levers provide a fixed movement ratio between the projectile end of the arm and the counterweight end of the arm. It also serves as the centerpiece of our trebuchet, allowing us to tack on things like slings and hanging counterweights. However, as I said earlier, a 1:4 arm ratio isn't going to throw anything very far on its own. To do better, you'll want a sling. Contrary to popular belief, slings are not just a convenient release system. They are an impressive energy transfer mechanism. Don't believe me? Watch this slow motion clip. Here the sling unfurls, stalling the arm and the counterweight. Most of the energy is in the projectile, making this a very good release point. The multiple rotations trebuchet is an extreme example that relies almost entirely on sling stalls. Shown in the simulation, the trebuchet undergoes several sling stall points before releasing. Since sling stall position is a major factor in trebuchet efficiency, here are some sling stall tuning tips. If you want an earlier sling stall, shorten the sling. If you want a later sling stall, make the sling longer. In conclusion, sling length determines the sling stall point. Before discussing the ideal sling stall point, we have to address an issue on the other end. A counterweight fixed directly to the arm is an energy hog. It's big, heavy, and usually retains a lot of energy at the bottom. However, medieval engineers had an elegant solution. They would hang the counterweight from the arm. Here's a slow motion clip. The beauty of this mechanism can be seen when I plot the motion of the arm and the counterweight. The counterweight falls almost straight down, stops, makes a sharp turn, and gets pulled parallel to the ground. This creates a counterweight arm stall point. Here, the hanging counterweight mechanism transfers almost all the energy from the counterweight to the arm. Syncing the sling stall point with this counterweight stall point results in a very efficient throw. Note how still everything is at the end. Be warned, past our counterweight stall point, the counterweight actually pulls against the arm. While it's okay to release slightly after the stall point, don't release too far after. With this in mind, knowing how far to hang your counterweight is very important. Here's how to find the stall point for a given hanging counterweight length. Hold the counterweight in the launch position, then pull it straight down. When you can't pull down any further without moving side to side, you are at the stall point. This is an okay length. For reference, here is one that is way too short. You are not going to get a good release off of this. Of course, the hanging counterweight trebuchet sacrifices fall distance for this efficiency. This means that it isn't viable for height-constrained competitions. There are several modern designs that you should look into. The floating arm trebuchet uses rails to constrain the counterweight vertically and to allow the arm pivot to move horizontally. This has a counterweight stall when the arm is vertical, but doesn't trade off fall distance. I highly recommend this design for a wide variety of efficiency contests. Multiple rotations trebuchets are actually surprisingly efficient if you can get the sling stall points right, and they have a certain novelty factor. Unfortunately, they are very unforgiving. Here is an interesting twist on hanging counterweight trebuchets. From what I have seen, the nicest ones have wheels or a floating arm. There are many other variations, but I don't have time to discuss them. If this video was useful, please like, subscribe, or check out some of my others.